Okay, so I want to go ahead and do a real quick video going over the code for my binary search tree. I'm going to be adding a new extension to VS Code, kind of to do a little more illustrative aspect, see what's going on in terms of the classes and how the files interact with each other. Nothing too fancy or anything, I don't think, but hopefully adds a little bit more of a in-depth look at how these files all interact with each other. But in terms of going over the content and context of the binary search tree, again, I have my other video that goes over the slides, and then I'll have one that has more of an illustrative aspect, so you're going to see a lot of the actual data, but not a whole lot of illustration of what's going on. Again, both of those two assets are going to be in two separate videos. This, I just kind of want to show the actual code and how the files all interact, because it's a little bit different than the previous ones we've done. So, real quick, let's just go ahead and swap over to my text editor and see we have our normal array of files. You can see here I have kind of this drawing area, which I will be using momentarily. But let's see, where do I want to start? I think we'll just start with the node. It's always the easiest thing to start with. So in this case, we have this typical pragma 1 that deals with actually handling. This is the only time you should see this file. Just some class stuff for C and C++, not a big deal. Then we have the actual class. We have some public aspect, and there's no actual private aspect to our node class, which makes sense because we want to have as much access to external classes for nodes so they can actually utilize them and all of their attributes. So in this case, we have some data. Again, we have the integer because we need to have left and right attributes for the children being less than and greater than the actual parent. So having some index data for that is going to be absolutely critical. And then we also have our left and right pointers for our children. And that's going to be about it for those. We also have default constructor, a constructor with an integer data attribute being added to it. And then we have, of course, our integer returned degree function. And we'll be able to find that right over here in node.cpp. So again, we're including node.h here. So it's all access to the node class, but this is going to be the actual function for degree. So again, we just have an integer set to 0 for child count, check if a left child exists, increase the actual count here, and then also check for right, increase and count there, and then return the possible value. It's not a whole lot going on there, but if we look at it real quick, once I find my pen and everything, we can see that we have, say, I don't know, can I move this? Right, so we have our node header, and then we'll have our node.cpp. Right. So this is going to be our first part of the class. So if I, real quick, I should be able to group these together. Kind of get them sorted. So we have node.h and node.cpp. So let's just take a look real quick. Put this here, and say that this includes node.h. So node.cpp is utilizing node.h, getting access to everything in it. They are kind of intertwined as its own class, but then come over to, we have our main here, and this is doing a few different aspects of our BST class, and it includes bst.h. So let's go ahead and take a look at that. So here you can see that bst.h is including node.h as well for everything it does. So let's take one real quick and go ahead and use, I guess, this, and do bst.h, not hj, like this, and maybe make that a little bit smaller. There we go. Right click, let's just group that, and we want to say that that is also including node.h. So if I I move this around. Yep, both arrows will follow it. So that is going to be BST is utilizing node.h. Node.cpp is also utilizing node.h. I'm just going to try and get this structured in a little bit better way. I think this might be the... Nah. I think this is good. This is fine. This is fine. Because, if we look at it, bst.cpp is also utilizing bst.h here. So we go back, then we'll need to create a rectangle, so text, bst.cpp, let's just group those together real quick. And so this is kind of what I do. bst.cpp is utilizing bst.cpp. bst.cpp is utilizing bst.h, bst.h is utilizing node.h, and then node.cpp is utilizing node.h itself. And then main.cpp is also including bst.h. So, real quick, one more right here. This, do main.cpp. Like so. That over here. And this is kind of the map that we'd have of our actual files. We have main.cpp, bs.cpp, node.cpp. This one exists in its own kind of area, but then you notice that bs.cpp and main.cpp are both utilizing bs.h, and bs.h itself is also utilizing node.h. So both of these files have access to node.h. Node.cpp has direct access to node.h, but it does not have access to bst.h. So this is kind of the actual map we'd have. Now I'll show actually how this happens for compilation whenever we get to compiling the files, so I'll come back to this later. There's a reason I did this. Now, getting back to our actual main code, we go back to our binary search tree well, let's do the H first. Let's just do our header first. So we include nodes, we have access to all of node, we include IOStream just to have some aspects of, say, cout, indel, just basically input-output stuff. Now notice that I'm actually including IOStream in bs.h. That means anything that inherits bs.h, anything that includes it essentially, has access to IOStream as well. So that's why I notice I don't use IOStream in either the main.cpp or the bst.cpp because it's already included here in bst.h, and I don't think it's not in node.h either. So we have access to IOStream via bst.h in this case, so no need to inherit it for main.cpp and bst.cpp. May not be the best thing to do, but I'm doing it for convenience here and just kind of illustrate how it works. So first, every single binary search tree is going to have a root. So one of the most important parts is to have some starting place for the binary search tree to begin. And then we have recursive calls to all of our functions, where this can be destructing the tree, that's our destructor, insertion, removal, all three forms of deletion, finding, and then all three of our traversals. From there, we're going to have our actual constructor, which just initializes root. That is the only variable to deal with, so we just have root set to null pointer. We're good to go. And then we have a destructor here, which will be a public call that will call destruct tree. Same thing with this insert, remove, find, in order, pre-order, post-order. They're all public calls that will call a private recursive function that does most of the actual brunt of the work. So moving on, we have bst.cpp, and here we have the public deconstructor. This will be called every single time that, well, if you call it manually, but every time that the class goes out of scope, whether you delete it or you close it, it will call the destructor, which will then recursively delete everything in the tree. So that's going to be a typical, if tree is empty, we just return. So, well, not if tree is empty, but if the node is empty, which happens if the tree is empty as well. So if your node is going to be a null pointer, there's something to do there, we just return. And then here we actually call destruct tree on the left side, then destruct tree on the right side, and every single time we're just going to delete our nodes and set them to null pointers, so deleting all the data subsequently recursively. Alright, so that's pretty much destructing. It's really not too hard. And then for insertion, same thing. Public call, that all it does is just insert something starting at the root. Here, again, if a node is going to be a null pointer, then in this case, we actually want to insert the data at that location and then return. However, if something exists at our current location, then we need to check if it's less than or greater than our current node's data, and then traverse the left and the right tree, or the right tree, depending on which. Okay. So go from there, we have remove. Again, this is the very, very fun one. So remove, first, check if your tree is empty. If it's empty, there's nothing to delete, just return. However, if there's something in it, begin the recursive call, starting at root. Here, in this case, check if your node's empty. If it is, nothing to do there, return from there. However, if some data exists, then the fun begins. So first thing to do is check if the data is less than. If it is, go down the left subtree. If it's greater than, go down the right subtree. You're going to do that for everything, basically. However, for removal in this case, if it's neither of those, and you already know that the data does exist, that means that you have found the actual data you want to delete. And then we need to actually figure out which of the three types of deletions we want to do, whether it be our 0 degree, our 1st degree, or our 2nd degree deletions. So we call the node's degree function, which will tell us how many children that particular node has. And that particular node in this case is the one that we want to delete. So if it has none, we call it 0 degree. If it has 1, we call 1 degree. If it has 2, we call 2 degree. So let's go ahead and start with the 0 degree deletion. That means it has no children. There's no big deal. Real quick, let me hop over here, page 2, and I'll sloppily draw up a binary search tree. I say sloppily. I'll try and do this in an actual decent way. So if I do this, and let's just do a few. Let's just do, whoops, this one, here, here, and then here. Okay. Now that, oops, this goes here, this goes here, oops, here, and then here. So let's just say that this is going to be a binary search tree. And I'm not going to do text here because that would take way too long, so I'm just going to do maybe a 20, a 50, 70, and then a, oops, that's not proper. That just looks terrible. 30. I did 10, and then here I will do a 5. So in this case, if I want to do a 0 degree deletion, that means I need a node that has no children. So the actual ones we can look at are our leaves. That's going to be 5, 30, and 70. These have no children, so I can delete them, no sweat. So if I want to, I just do this and do that. And I'm good. No big deal. Because all we're doing is we're deleting a node and setting that to a null pointer. Not a big deal. For 1 degree deletion, a little bit different. Here we need to create a temporary node at our current node as a reference to that. So let's say we want to delete, let's say I want to do 10. I want to delete 10. So I will create this with a 10 in it. Okay. And then we'll go back to VSC.cpp. Now it has all the other attributes, but I just want to get that one as 10 just to kind of make sure that that's known as the reference to what we are deleting. So in this case, we check for a left child. If it's not there, that means there must be a right child. So let's just take a look back. Whoops. there is a left child, it is 5. Okay, so that's good to know. So that means that node, our current node, is going to be equal to node left. So our current reference, in this case, here, is now going to be that. So real quick, we are going to put our 5 here. Now it has all the attributes of that. So we have overwritten that. I'm just going to get rid of that because it's the same thing. I'm so sorry, I keep thinking I'm tabbing out to a different program. And then we delete temp, and temp is going to be set to a null pointer. So then we just erase this, and here is my new binary search tree. We have 20, left child of 5, right child of 50, 50 has left child of 30. Now we move on to our 2-degree deletion. This is going to be a little bit more involved, a little bit more complex, in my opinion. We are going to be doing a successor-based deletion, or successor-based 2-degree deletion. There's also predecessor-based 2-degree deletion, which I mentioned that in the other video. I can actually do a version of it here. It's not a big deal. But right now, for successor, actually, I'm just going to keep it simple. Just keep it successor. I'll show what predecessor is in the other video for actual illustration. But for now, we're just going to do successor-based deletion just to keep this simple. So, first things first, create a temp node set to our current node's right child. So in this case, we want to delete 20. So I will create a node here. 20, just to indicate that this is the same thing over here. Not a big deal, it is just a reference. So sorry. And then we have, while temp left is not equal to a null pointer, temp equals temp left. Now I'm going to make an alteration real quick. I am going to add another left child here to illustrate what I mean a little bit better. We'll make this 25. Okay? So I'm also very sorry. This needs to be 50 because it is a temp set to our node's right child. We want to delete 20. So delete 20. Okay? So this is a temp node for our right child. Then we want to get temp left. While it's not a null pointer, we're going to continuously go down until we get to the last left child of our right subtree. So that's going to be 50, going to 30, going to 25. So we end up at 25. Right? And then we say that node's data, which is the node we want to delete, which is 20, we're going to set that equal to temp's data, and temp is now our last left subchild, or child of the right subtree. So real quick, we just adjust our data, 25 there, and then we're going to recursively remove on the right subtree until we find temp data, which if you recall, temp data is going to be temp data is going to be 20 because it is the last, well, not 20, 25, I'm so sorry. It's going to be the last left subchild. So we will just simply recursively delete it, and it's going to call a 0-degree deletion because 25 has no children. So that's fine. It's not always going to be a 0-degree deletion because maybe in a case we want to do it again here. We want to delete 25, so let's just go ahead and retry that. So let's just change this to deleting 25. I don't know why it's got this different cursor. It's a little bit weird, so I'm sorry. So delete 25, we're going to do the same thing. Create a temp reference of, sorry, I'm doing this a little bit lazily. Oh my goodness. There, that's way too large, but it doesn't matter. It's 50 right now, and I want to create a 40 here. Okay, so I want to delete 25. So this has 2 children, so I need to do a successor-based deletion. So 50 is going to be my right node from my actual node. So we get node right, so right subtree, and we're going to go until we get the last left child. Last left child is 30. Yes, 30 has a child of 40, but we don't care about that right now. And you'll understand why in just one second. So what's going to happen here is we're going to, first down here, our temp then becomes 30. Our root to become 30 because we're going to copy data from here up to here, and then we are going to do a deletion from the right subtree 50 down until we get to temp, which is 30. We're going to do a deletion on 30. This is not a 0 degree deletion. This is going to be a 1 degree deletion, so we're going to end up doing something kind of like this. We end up with 5, 30, 50, and 40, which is still a perfectly fine binary search tree. So this is the best illustration I'm going to do for this, and then we can move on. I'm not going to do a illustration on finds and find recurses. I wanted to do that for the binary search tree deletions just because it gives me some actual talking points on some of those differences there. Now, find's pretty easy. Again, check if your binary search tree is empty. If it is, return. If it's not, go ahead and start finding from the root. Here, we're going to actually recurse down. If node is null, then we return up from there, from the recursive call. And if it's not, then we found some data. Now we need to see if that data is correct. If it is less than, go down the left subtree. If it is greater than, go down the right subtree. And if it's neither of those, then you found it. So you just return true. And that means, hey, you found the actual data. Cool. And then we have the actual traversals, which again, post order, just go ahead and start at the root, and then return if null, traverse down the left tree, traverse down the right tree, and then handle your data. In this case, we're just printing out. For in order, go ahead and start at the root, return if null, traverse down the left tree, then handle your data, and then finally traverse down the right tree. And then for pre-order, start at the root, return if null. First here, you're going to handle your data, then you'll go down the left subtree, and then finally go down the right subtree. I just realized I forgot to compile and run the code, and I promised to do that, so let me go ahead and do that real quick. Let's go ahead and do the main real quick. So I kind of want to show the relationship between the CPP files, header files, how they get compiled, just at a very, very high level, just so there's some actual clear understanding of that. So let's go ahead and look at main real quick and see what's happening. So we're inserting a 56 into this newly instantiated binary search tree, which is a very, very descriptive name. So we have 56, it's going to be the root. 34, it's going to go left side, so it's obviously going to be the left child. Then we're going to insert 70. After that, we're going to remove 56. Actually, you know what? We'll remove the 56 here. So if we do the in order, you'll see how it gets printed out in order, and then we'll do removal of 56, which is going to call a 2 degree deletion because it's going to have two different children. And then we'll have in order again and print that out. So real quick, let me see. I'll do terminal. Now normally what I do, what you'll see me do in these videos is clang++, which is just my compiler for C++, and then I have asterisk.cpp. This is a wildcard, which basically means anything in the current directory that is a CPP file. But what you can do, let's say we do main.cpp, and then I want to do node.cpp, bst.cpp, and I'm going to do -o. This is going to be, let's just do bst.out because I can't think of anything more to script. Now you can see we have an executable file of bst.out. So it's just binary, it's just a binary file, so you can't display it or anything. but we've compiled it. So essentially, if we look back here and we go back to page 1 real quick, out this, then you'll see that we have node.cpp is inheriting node.h, it's including it. bst.cpp is including bst.h. main.cpp is including bst.h, and both of the bst.h itself is including node.h. So that is kind of how they all correlate to each other. But we need to actually say that the compiler needs access to node.cpp, bst.cpp, main.cpp for that particular command to actually work. Or if you're me and you know that this works and you're just being lazy, you just wildcard it with .cpp and it's going to inherit all of them. There's no need to include node.h or anything like that. Those are included in the files as reference to headers, so you don't need to actually include them when you're compiling. You just do this, and you'll see it's going to compile. It's a.out, that's the default for CLang and G++ and stuff like that. It's not a big deal there. But let's go ahead and run that bst.out, and you'll see 34, 56, 70, that is my in order, and then we have 34 and 70 once we delete 56. If I do a.out, it also does the same thing. But if we come over to main.cpp, and we say, I don't know, I just think it's some arbitrary data. I'm actually not even going to look at the keyboard. So we got 56, 34, 70, 49, 17. We have remits remove. We're going to do a pre-order and post order. So we'll just compile this. So let's make it out. So again, if I run my bst.out, I compiled that before I made my changes, so it does 34, 56, 70, 34, 70. Now if I do a.out, which is going to have my new changes, you'll see 56, 34, 17, 49, 70 for pre-order, 17, 34, 49, 56, 70 for my in order, and 17, 49, 34, 70, 56 for my post order. So that's kind of how compilation works. I wanted to touch on that, and I completely forgot whenever I was recording the previous parts of the video. I do sincerely apologize for that, but I'm going to make sure I add it in through an edit, so this all get compiled together. As it looks like it's going to be 3 different parts of the video, but hopefully everything makes sense here, and we'll get back to the actual main video right now. So there's not a whole lot going on here, honestly. It's a lot of recursion, but it's based on the same principle of the left child is less than the parent, and the right child is greater than the parent. And that is how we structure our data. Now, again, I understand the fact that recursion in general can be a little bit finicky, and it can be honestly a little bit clunky at times. It is not the end-all be-all solution for quite a lot of things, because you're going to end up with a lot of overhead. One of the aspects of binary search trees that is really bad is when you get an unbalanced tree. That means that you're going to end up a long time on a particular side of the tree as opposed to the other side where your data could be, and that becomes almost as inefficient as a singly linked list, because you're going in one direction when you need to be going in the completely other direction. But we have balanced trees for that, the use of AVLs. So there are caveats to binary search trees. There are ways around them that are a little bit more convoluted to set up and a little more involved in computation. But overall, I think they're pretty good. Obviously, there's a lot of nonlinear data structures, but this one's a pretty good one. Same thing with like linear, has stacks, queues, linked list. All of them have their own use case for some particular reason. But that's me for me. I hope you guys learned something. I'll see you guys in the next one. Bye.